So the same thing. We have two balls. They're identical, and they approach with a velocity like this. Let's make this guy a little bit longer because it's 12, right? That way it's easy to visualize. And the coefficient of restitution was 0.9. And we want to find the magnitude and direction of each ball after it's when it separates. Okay, so maybe we can draw a diagram, something like this. Well, things are getting complicated, right? We have more particles coming in and more times, but let's try to make this as simple as possible. Okay, so this for these guys, and that's for that. Okay, so this here is the velocity decomposed of the green ball, and this is the velocity of this purple one, and it's before it meets and come together, right? And this is what happens when at the right moment when they meet, and there are forces or impulse we can think, and then right after they separate from each other, we can also decompose the velocity like that. Okay, and once you add these things, think about this one and that one. It's the impulse and momentum and impulse principle, right? We have momentum before the impulse, then you're going to have the later case. This is the initial momentum, and you add an impulse, then you're going to have your later momentum. Okay, so I hope this kind of visualize what's going to happen in this kind of collision case. And we know what these VA X1, VA Y1, or these guys are, because the initial velocities are provided. So let's find those first so that we can use that for later purposes. So, and let's call this guy A and this guy B, by the way. And of course, we are having that X and Y defined like this. So for VA, it was 9 meter per second and had 2 velocity components we can decompose into, right? And that was 30-degree angle. So VAX is going to be 9 cosine 30. This is VAX, right? And that is going to be 7.8 meter per second. VAY is going to be 9 sine 30, and that's going to be 4.5 meter per second. All right? So that's that. And we have VB as well. And VB was velocity that was going up like this, right? It was 12 meter per second, and it had an angle of 60 degrees. So this angle here is 60 degree, right? And because, or yeah, let me just write this down, VB, VBY, and that is going to be negative 12 cosine 60, because this velocity cosine 60, and that becomes a velocity pointing towards the left, right? So you need to make sure it's a negative value. Okay. That becomes its -6 meter per second. Let me put a highlight that way. You don't forget about that part. If you mess up with these plus and minus values, your answers are going to be totally different. So you need to really take care, be careful about these polarity. Okay, and it's sine 60. I'm talking about this value, right? That's sine 60 times 12, and that is going to be 10.4 meter per second, and it's going to be a positive value because it's going up, right? We have defined our axis to be like this. So pointing towards the right is going to be a positive value. This is pointing right, so it's a positive. This guy is pointing left, so that's a negative value, right? And what else we have to consider? We know that MB and MA are going to be the same, and let's call that M to make it simple. So these are kind of the information you can find out from the problem that is given, right? Okay, so having those in our pocket, we can approach this. Let's first think about the momentum. So momentum, we can think about the first particle A and the second particle B. And in the first particle, we also have X and Y direction, right? So let's think about X and Y, which is going to be MA, VA, X1 plus negative F delta T equal MA, VA, X2. Impulse momentum thing, which is here. So MV plus the impulse is going to be MV in the X direction, which we got that here. All right. And in the vertical direction, there's no vertical force. There's only the horizontal thing, right? So this is going to be just the same as that one. So MA, VA, Y1 is going to be same as MA, VA, Y2 because there's nothing there, or it's plus 0. So from here, we can clearly think this MA, they're the same. So VA Y1 is same as VA Y2. That's one, one thing we can identify. And by the way, that is given as VA Y1 is what? 4.5 meter per second. So this is going to be 4.5 meter per second. We just got that. So this guy is solved here, all right? Then we do the same thing for particle B in X and Y direction. So X is MB, BB, X1 plus F delta T is MB, BB, X2. And in the Y direction, same thing, MB, VB, Y1 equal MB, VB, Y2. It's like a tongue twister for me. Excuse me. So same thing here. These two go away, and we can find out VB Y1 equals VB Y2, and that is 10.4 meter per second. So we just got, let's use a different color maybe. Do we have other colors? Yeah, let's use that here. So we got this, which is MB Y2. So we got that one here. And let's move on. So from the momentum, we got actually 4 equations. But these two, let's see what we can use that for. And if we consider both A and B together, which is going to be the conservation of momentum, in other words, the summation of these two, MVX, MAVA plus MBVB is going to be same as MAVA, MBVB in time 2. So if we do that thing, the conservation of momentum, MA VA x1 plus MB VB x1 equals MA VA x2 plus MB VB x2. And well, these are all M's. They're all the same thing. So we can just, get rid of these all. That is going to be MVA x1 was what? It's 7.8, right? So 7.8 plus VBX1 was -6 plus -6 equals VAX2 plus VBX2. These are the only thing that we need to find out, right? And that's that. So from here, we can tell VAX2 plus VBX2 equals 1.8. So we have one equation that's kind of the candidate for the next step, right? And we can also think about the restitution. So, oops, what's going on? So the restitution, which is E separation velocity divided by approach velocity, right? And that is going to be VBX2 minus VAX2, VBX1 minus VAX1. Make sure, again, it's separation divided by approach, and separation is time 2, right? So you want to have the subscripts 2 on the top and the 1 at the bottom. And if you have the subscripts across each other in this way, then you're going to be safe. Okay, so it's going to be 0.9, and that's VBX2 minus VAX2. And VAX1 was 7.8 minus VBX1 was -6. So from here, we get another equation, which is VBX2 minus VAX2 equals, we just do this and move it to the left, then that is going to be 12.42. And here we have another equation. And we can think, oh, it's AX and BX, BX, AX. So we have 2 equations, 2 coefficients. We can easily find out the values, right? So by doing a little bit of math, so let me use these 2 together. We can have VAX2 equals minus 5.31 meter per second. VBX2 equals 7.11 meter per second. Alrighty, so we just found a VAX2 and VBX2, and we can highlight that with some other color. Maybe we can use green, or green is already used, so use this brown color, which is given there. Well, this is pretty colorful, but eventually I just wanted to show you these all four are obtained in these corresponding locations. So later on, if you just follow this color thing, you can go back and trace how you get which one, okay? So last step, if we just visualize what happened was, so there are two balls, they come in like this, 9 meters per second, and it's going in like that, 12 meters per second. And this has 60-degree angle, this had 30-degree angle, right? So they met up like that, okay? And after, when they separate, it's gonna separate like VAX1, X2, VA, let's just try that, VAX2 and VAY2. Okay, so it's going towards the left about 5.3 and going up 4.5. So it has this kind of direction and value, right? And what's the for the Y? Y is 10.4 and 7.11. So it's 10.4 going up like that and 7.11 going to the right, maybe like this. So 10.4, 7.11. So that's VB2. This is VA2, right? So those two were coming in like this, but when they separate, they're going out like that. Okay, so from here, if you want to find the angle, you can easily find that as well. But I just wanted to, instead of just getting these numbers, I want to, show how these are coming in and separating. That way you can have a little bit more of physical intuition, okay? If you just get these numbers and ditch it, then, well, probably nothing is left, okay? So when you also study by yourself, try to, visualize these kind of images, what's happening. These mechanical stuff, you can kind of think about how things are moving, and that really helps you to, when you're working in the field, okay? So that's that. And let's try another one. Let's see. And this one, I don't know why I deleted all the questions. So the tennis ball. So the situation here is this lady is hitting the ball, serving, right? And we assume that the exit velocity of this ball is not angled or it's not going up like that. It's just horizontal, okay? That's kind of the assumption. It's served horizontally and it's 2.5 meters above. So this is 2.5 meter, okay? And it strikes the ground here, and this ground is smooth. So there's no friction or anything on the horizontal direction, okay? So you can imagine the velocity that comes in and go out, it's gonna be the same. Only the velocity in the vertical direction might change. And that coefficient of restitution was given as 0.7. And we want to find out what this VA was and what this BV is right after the rebound, okay, for this guy. And this is 6 meters. So first, we can, if you're not interested in this velocity VB, in our previous chapters, we talked about the velocity at this point, right? The velocity when this ball hits the ground. I think I asked you that in the midterm as well, right? The home run ball and what was the velocity when it hits the ground, right? So we can think about this problem as a two-part thing. So there is going to be a velocity that hits the ground, and let's call that VB0. And then, so this here is one thing, and if you just focus on this part, there's an angled impact, right? The ball is approaching the wall or the ground with an angle, and then it bounces back. So this part is something like impulse and momentum, that kind of business. And here is more like kinematics, or how do you call that? That energy or projectile movement, etc. Okay, so maybe I can just highlight that. So here is one thing, and this is a projectile movement. And what happens at this point, that's a impact kind of thing, right? So let's, having that in mind, let's approach this problem. And so first, let's talk about the projectile. By the way, when I switch these colors, don't really like mind, like think about what's the meaning of red and black or blue. I try to be consistent, but just when I write, the colors are changing randomly. So generally, it doesn't have a big meaning in what I use for red and what I use for blue, just for information. Okay, so anyway, if we first think about this projectile movement of the ball, so it was hit, or it has an initial velocity on the horizontal direction, and this is flying down and it hits the ground. That's it. So we can, of course, we do this axis thing first, and the displacement in the y direction, that is going to be S naught plus VA YT plus 1/2 GT squared, right? And we know when the ball hits ground, it's going to be 0 equal, because the vertical direction, vertical displacement was 2.5 and it decreased down to 0, right? There's no vertical thing. So that is going to be 0 equal. The initial displacement is 2.5 plus, what's the initial velocity in the vertical direction? There's nothing, right? So it's 0 times TB plus 1/2. G is negative 9.8, right? And TB squared. Okay, so from here, what we can get, it's like 4.9 TB squared is 2.5. Is that right? Yeah. So we can know TB is equal to 0.71 second. And then that was the y direction. And what about the x direction? X direction is S of x is equal to S naught plus VAX times T. And when it hits the ground, we call it TB. Then when it hits the ground, this is going to be 6, because it was here. We can call that 0, and that flew for 6 meters, right? And 6 equals S naught 0 plus VAX times TB. And we know TB is 0.71. So VAX is going to be 6 divided by TB. That is what? It's about 8.45 meter per second. Okay. So we got one thing that is needed. We want to find VA, and that's just this guy. And we also would like to find the velocity at this point, right? So we can also find the velocity VBOX, and that is actually going to be VAX, right? There's no horizontal force, so this velocity is just preserved at this moment. So it's going to be the same like that. And VBOY, it's going to be, how should I do the things? V naught plus G of T. It's going to be something like that, right? And V naught is, it's 0. There's no initial velocity along the vertical direction, along the y direction. So this is 0. So 0 plus minus 9.8 times TB is 0.71. And that is going to give us something like -7 meter per second. And this is 8.45 meter per second. Okay, so we got these, which is the velocity when it hits the ground. The horizontal component is going to be 8.45 meter per second, and the vertical component is going to be 7 meter per second. Okay, so that is the velocity when it hits the ground. But what we want to find out is when it bounced back. Okay, so we're now going to only focus on this part here. So if I just draw that down one more time, we have a surface, right? And here's a ball that is about to hit the ground, right? And after it bounces back, probably it's going to move like this. So we would like to find what are these components. And actually, we know the horizontal and vertical component of velocity. That was obtained as 8.45 meter per second. And this one, -7 meter per second, which means it's going downwards, right? And that was 7 meter per second. Okay. So, and we assume that this floor ground is very smooth, so there's no friction applied when this ball hits the ground. So, one thing that is very obvious in this case is this velocity is preserved. So, this guy on the horizontal direction is going to be 8.45 meter per second without any change. So all we need to find is the velocity on the vertical direction when it rebounds. So that one can be obtained by using the coefficient of restitution. So E is going to be approach velocity over separation velocity, right? And that can be seen as VBY1, VBY2. If we call this guy as VBY1 and we call this VBY2, y2. Okay, and well, why now I use the space a lot over here. So E was given as 0.7, right? So if we use that number, 0.7 equals velocity going in, coming down in was 7, and velocity that goes out is going to be VBY. And VBY is going to be 4.9 meter per second, like that. So we can find this thing out. Finally, how this ball moves is it has a horizontal velocity of 8.45 meter per second, and the vertical was 4.9 meter per second. So we can find the angle and the magnitude, right? So the magnitude of the ball after it hits the ground is going to be 4.9 squared plus 8.45 squared. And that is going to be about 9.77 meter per second. And if you're interested to find this angle, tangent theta is going to be 4.9 divided by 8.45, right? So you can find theta, that is about 30.1 degree. Okay,